For the past 6 months or so, I've been creating a tool I call Orbit Engine. In short, it's a simulator tool with a graphical user interface that lets you simulate highly accurate multi-body orbital systems. With this, I'm able to simulate for multi-body systems, and that means instead of only the sun's gravity having an effect, every object's gravity affects every other object. Orbital dynamics simulators have been done before. In fact, I've designed one before in a game engine and presented that at a science conference. But what makes Orbit Engine stand out is how I developed it, and how easy it is to use, and how surprisingly fast and accurate it ended up being. Why did I do this? Well, I really like physics, and I especially like astrophysics, and I'm also a game developer, so physics simulations and orbital mechanics are kind of the perfect combination of everything I like, and it makes for a really cool research project on investigating simulation algorithms and orbital motion. I even plan on publishing this work on a peer-reviewed journal later on. So that's what this video is about. First, I'll talk about how to use Orbit Engine to interact with the GUI. Then I'll talk about the details of the math and physics behind the functionality of this tool. Next, I'll talk about the tests I've conducted to demonstrate the accuracy and speed. And finally, I'll discuss where this project could go in the future. First, a demonstration of Orbit Engine. So run this GUI_universal script to access the default interface. Once you're here, you can look at the top right, where you can input initial conditions like position, velocity, and mass. The units for position are in astronomical units, and the units for velocity are in AU per day, and the units for mass are solar masses. So let's just create the sun. These are the initial conditions I'm using, and here we're assuming that the sun is at the center of our system, and it's also moving at 0 velocity relative to the reference frame. So the position and velocities are just 0 vectors. And the mass of the sun is 1 solar mass. So once you press this generate body button, it generates the sun and is now in our simulation. But a simulation with just the sun is kind of boring, so I'm going to add the Earth. So the Earth has these initial conditions. It's roughly 1 AU away from the sun, and it is traveling at around 0.017 AU per day. So once you press the generate body button again, the Earth is now generated, and we can now run the simulation. And as you can see, it barely took any time. We can then plot the results here, and we can view it in 3 dimensions. But just looking at the plot is also kind of boring, so we can press this button here to animate the results. If you want, you can also change the animation settings here, like how long each frame takes and how much the data is split. So this is an example of both of these settings coming into play. And if you press this button here, it resets the simulation, and so now there's nothing in the simulation for us to simulate. We could re-enter all the values, but I also added a method where you can just pull all these initial conditions from a CSV file. So let's take this one, for example. So if you put the full path name in this input field and then press this button, this would now add the bodies to the simulation. And so if you press run simulation again, the old plot is still animating, but now if we plot the results, it will now be the new plot. And we can animate these results again. And this is a Earth-Moon system, so you can see the moon kind of orbiting around the Earth. We can also track these bodies in the simulation by pressing this button, track body in animation. So this is right now tracking the sun. This is tracking the Earth, and now it's tracking the moon. It's back to tracking nothing, and now tracking the sun, Earth, moon. And, well, this button doesn't always work perfectly. Right now it's working pretty well, but it's also a pretty buggy feature. And so I'm working to improve this, but right now it works pretty well. And it's especially cool when we get into some more chaotic systems where this tracking is actually really useful. Now, I should probably take some time to explain the simulation settings section over here. So we can configure the simulation settings by changing the time step, duration, and the R-toll. By default, the time step is 0.0001 days, and the duration is 365 days, and the R-toll is 1 times 10 to the negative 9. Now, this time step means that for every single 0.0001 days, there is a new data point being generated. R-toll is a measure of relative error allowed for the ODE solvers. It is a measure of the error relative to the magnitude of the solution. Thus, a 1 times 10 to the negative 9 R-toll means that the solver only allows a 1 times 10 to the negative 7% error relative to the overall magnitude of the solver. In our example just now, it was 1 AU. Conversely, A-toll is the measure of the absolute error allowed, irrespective of the magnitudes of the solution. Now let's simulate some bigger systems. We can pull the solar system into it, and we can run the simulation. Again, doesn't take very long, and now we can plot it. So this is a year's worth of the solar system being simulated. We can animate the results again, and well, we can zoom in with the plots tools. But we can also track the body in the simulation, and this is where the tracking feature is kind of especially useful when you have many bodies in this simulation, so you know what you're looking at here, and it works pretty well as well. So yeah. So what if you wanted to create something more chaotic, like this 4-body chaotic system? If you pull it from the CSV, run it, we can plot the results, and as you can see, we have a pretty chaotic orbit right here. We can animate the results again, and then track the planets in the animation, or track the bodies. And well, as you can see, we can seamlessly flick between any body and that are chaotically influencing each other. So yeah, it works pretty well. And I guess this is where the tracking feature really shines. It makes the simulation look really cool. So now I'm gonna attempt to make a binary system with the sun, a star of a mass of the sun, and another planet with the same mass. And well, we have this interesting little binary system here. So we have this simulation here. If we want to save this for later, we can name this binary star.csv, and we can save the bodies to the CSV file. And then if we close the app and run it again, if we typed in the same name, it plots the exact same orbit, which is pretty cool. Now, you might want to use this orbit data that Orbit Engine generates. So just type in the path name that you want to use and save the orbit with this button. And then after that, it should show up in the path and look something like this. The first 3 columns are the XYZ positions. And so that's basically the tool summarized. In the next video, I'm going to be explaining how the tool works with the math and the physics and the code. Thank you for watching.